Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will continue talking about capacitors. We will explain the last type of capacitor, a spherical cells capacitor, and find also its capacitance in terms of the different variables we have on the system. Also, we will relate capacitance with the energy that can be stored in a capacitor. And finally, we will understand how dielectrics affect these situations. So, let's start! Alright, let's try and analyze this capacitor. If you remember from the video about Gauss' law, applications of Gauss' law and the spherical symmetry, we found that the electric field of this system of spherical cells, know that these are spherical cells, was kq over r squared in the r hat direction in between both cells. On the inside was 0 and on the outside was also 0. Also, on our past video, we found about electric potential, we found the difference in potential of these two cells, which are kq 1 over a minus 1 over b. And we see that this value is positive as b is bigger and therefore the whole term is smaller. So we have a positive value for potential right over here, and we are going to express it in terms of epsilon naught as we have expressed all other capacitance values in terms of this variable. So it will be q over 4 pi epsilon naught 1 over a minus 1 over b. Now we know that capacitance, as we found in our previous video, equals q divided by the change in potential. So what we are going to have is q over 4 epsilon pi epsilon naught 1 over a minus 1 over b. And now we can make some cancellations over here with the q's, and we find that the capacitance value is going to be 4 pi epsilon naught divided by 1 over a minus 1 over b. And what we see over here is that if the two radiuses are the same, capacitance almost goes to infinity. And if, for example, the radius of b goes really high, capacitance decreases. It's important to remember that this is where the formula for the capacitance of a spherical capacitor comes from. However, spherical capacitors are not really that useful because it is really hard to interact with the inner spherical cell without disturbing the whole system. Alright, let's try and understand what is the energy stored by this type of capacitors, and in general by all capacitors. Recall that voltage is related to charge in the following manner. We also know that in general U it's related to electric potential. Electric potential energy is related to electric potential by this relationship. If we are trying to find a small chunk of electric potential energy, we will have the electric potential energy that a small q feels, a small charge on this system feels at that electric potential. However, we already know that this electric potential equals the charge over z. So we're going to have q over c dq. And now we may integrate this, so we know that the integral of du equals the integral from q equals to 0 to the actual charge we have of the charge divided by the capacitance dq. And we find this to be 1/2 q squared over z. Well, actually big Q squared over z. Now, we know that in this situation, Q over C as we found it, equals the change in voltage. Therefore, what we are going to express, and it's actually the magnitude of the change in voltage, we're going to express this quantity totally in terms of the change in voltage, such as the energy is going to be equal to 1/2 times the capacitance times the change in voltage squared. And this is going to be a very important formula in general. Now, we actually know both the capacitance and the electric potential in this system, so we'll plug it in to see what happens. From our last video, we know the capacitance equals the area of the plate times epsilon naught divided by the distance. And we also know that the difference of electric potential equals the electric field squared and d squared. So we see some cancellations that are going to happen over here. We have the D, and that's it. And we're going to express this in the following way, as U equals 1/2 epsilon naught times the electric field square times D and the area of the plate. And if you realize, this is equal to the volume on which our capacitor, the volume our capacitor has. So this is 1/2 epsilon naught E squared times the volume of our thing. And what we find is that this kind of acts as an energy density, because we are multiplying this factor by a volume to get an energy. Therefore, we're going to define a quantity that is going to be the energy density and the electrical energy density, because we will get a magnetic energy density, and it's going to be defined in this way. And it can be proven that in general, the small amount of energy that is going to be at some place, it's going to be this energy density times the volume. And this is a very special relationship. In this case specifically, what we have found is that the energy density is constant, because the electric field all throughout our system of capacitors is constant, and that's why we get actually outside of the integral a volume multiplying. But in general, it can be proven, but it is outside of the scope of this series of videos, that this is the energy density for any electrical field. And that will be very useful when analyzing how energy moves in different circuit components. Alright, now let's explore dielectrics. Dielectrics are some insulator you put in between the two plates of a capacitor, and it has a very important effect, and that is that it changes the capacitance and it, depending on the convention you are using, it changes either Q or the voltage. So it changes one of those two things. There are conventions in which sometimes you are going to assume it changes Q, and conventions in which sometimes you are going to assume it changes the voltage, to take into account this effect. So what happens when an insulator is applied some charge? We have two different situations which actually end up becoming the same. Imagine we have water. You know, water is made up of some dipoles, so I'm going to draw them over here. So water is made by dipoles, and when an electric field is applied in this direction, for example, the dipoles align with it in such a way that they become this. And each of these dipoles now generates some sort of a small field in that direction that counteracts with the field that you already had, and therefore they make the field weaker. if you have some matter that is not made of dipoles, imagine it was just some chunk of matter that has whole atoms that are neutral, what is going to happen is that when the field is going to be applied to that, the atoms are going to become mini dipoles. And now, once again, with a much lesser effect, this is going to also interact with the electric field and make it weaker. So if we put any insulator, any dielectric, which is what these things really are, inside these two capacitors, the effect that it's going to take is that it's going to make this thing weaker. So the electric field we're going to end up having, E, it's going to be the sum of the electric field we would have without any insulator, any dielectric, plus the electric field generated by the induced charges. In general, this is summarized in the following way, as taking E naught and this constant 1 plus E induced over E naught. And this is going to be a constant, actually 1 over a constant, kappa, which is going to be our dielectric constant, in such a way that it relates these two quantities, the electric field and the electric field without an insulator. And what we see, it has a weakening effect. Usually, this electric field, E, is going to be proportional to K in every situation, which means that this is proportional to 4 pi over epsilon naught. And what happens is that we are going to include the effect of this kappa, of this dielectric constant that we have. We're going to include it in the permittivity of the space that is going to become the permittivity of the material we are treating. So in general, what is going to happen is that we are going to have a transition between epsilon naught times kappa that is going to become epsilon. So in all the equations where we had an epsilon naught, now we're going to have an epsilon that is equal to this dielectric constant times the epsilon naught. This causes that our C, which we have found that almost every time we have expressed it as a multiple of epsilon naught, is now going to be, this is going to be Z naught, is now going to be a multiple of epsilon, and therefore C is going to be kappa times Z naught. Furthermore, we know this is going to be equal to Q over the voltage, and here's where we have the choice. We either express that kappa inside of Q as Q being equal to kappa times Q naught, or we express that kappa inside of B, which will give us that B equals B naught over kappa. Some examples of values of kappa we have of this dielectric constant, and I'm going to write them over here, are the following. For vacuum, it equals 1. For air, the value is 1.0 something, and there are some decimals over there. For example, for water, this value reaches 80. And there is some other examples, such as paper with a 3.7, or Pyrex glass that has a 5.6. And this is the effect that dielectrics have, and they are really important to take into account when, for example, you have water in here. Usually with air, even though the value is not actually 1, it's 1 point something, we usually ignore them because the effect is really small. However, when we take some insulators that aren't as good, we're going to have this effect, and it's really important to take it into account. I hope you understood everything and also got a more complete sense of how capacitors work. the energy they store, also spherical capacitors, which aren't really that useful in real life, but they are a useful mathematical construct. Furthermore, you got a sense about how this dielectric thing that is actually fairly complicated behaves, and you just understood it more or less because we are not going to use it that often anymore. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!